Greetings, mathematicians. Welcome to this narrated PowerPoint on statistics, bivariate data, and scatterplots. Well, now, in grade 11 and grade 10, when we did statistics, we typically looked at one kind of variable at a time. We might have looked at a whole lot of people's weights, we might have looked at a whole lot of people's geography marks, we might have looked at a whole lot of people's shoe sizes, but importantly, we did it one at a time, one piece of information at a time. Bivariate data, on the other hand, is when we look at two sets of variables at the same time. And the reason why we do this is to see if there's any sort of connection, any relationship or association between those two sets of variables. So, for instance, here we have a table where we have the heights and the weights of several people listed. So, for instance, person number 1, their height is 162 centimeters and their weight is 52 kilograms. Person number 2, their height is 178 centimeters and their weight is 60 kilograms, and so on. So we've got 10 people there. This is probably me somewhere around there. Yes, ladies, I'm over 6 foot. Anyway, moving steadily along. So we have a table with 10 sets of people's heights and weights. This is bivariate data. We've got two variables that we're looking at the same time. Now, in order to analyze bivariate data, there are many methods of doing it, but the method we're going to start with is a graphical method called the scatterplot. The scatterplot. Thank you. So, what is a scatterplot? Well, we take our data and we're going to plot the height and weight of each person on a Cartesian plane as if these were x and y coordinates. So we're going to treat the height as if it's an x coordinate and the weight as if it's a y coordinate and plot them on a Cartesian plane. So it's going to look something like this. This is one I got a computer program to generate for me. Now when you do a scatterplot, you don't have to do little crosses for each point. You can just put a little dot. But what I did is I looked at this person number 1, and I said, let's treat this height as an x coordinate and the weight as a y coordinate. So where would that be on my Cartesian plane? Well, a height of 162 is over here somewhere, and a weight of 52 is over there. So this person here, that is their point on the scatterplot. Then we move to the next person, and we say, if they have a height of 178 and a weight of 65, the height of 178 is going to be somewhere here, a weight of 65 is going to be somewhere there. So this person is here. And then we look at this person, what is their height, what is their weight, plot them on our graph so that that person is there. Now you will notice with my axes I haven't gone all the way down to 0 because that would leave us with quite a lot of empty space. The lowest height altogether is 156 centimeters, so there's no need to go much lower down than 150. Likewise with the weights, the lowest weight was 52. There's no point going less than that. Otherwise we end up with a lot of empty space on our graph and a tiny cluster of dots up in the corner. So this is our scatterplot. There it is. Now, once we've plotted our scatterplot, we can look at it and see whether there is indeed any sort of association or correlation between the variables. And the way we do this, we look at all the dots and see if together they form some sort of line. Now, here's another example of a scatterplot, and you can quite clearly see that all these dots are forming a diagonal line, all right, going from low on the left up to high on the right. If dots are clustered in this pattern like this, forming a line that goes up to the right, we say that there is a positive linear correlation. Linear because it makes a more or less a straight line, and it's positive because it's going up to the right. Now what this would be telling us is that as one set of data is increasing in value, the other set of data also increases in value. So a real life example might be if the x-axis represented people's maths marks and the y-axis represented people's physics marks. You would probably find that the higher marks people get for maths, those kind of people are also likely to get high marks for physics. There is a positive correlation between maths ability and physics ability. The better you do in maths, the more likely you are to do well in physics, and vice versa. Alternatively, your dots could form a pattern like this. Again, they are forming a line, roughly speaking, but now this line is pointing the other way. So it's pointing down to the right. We call this a negative linear correlation. Linear again because it's more or less forming a straight line, and negative because imagine if you think of a straight line on a graph, a straight line function that has a negative gradient. Which way does it slope? Well, it slopes that way. So a negative correlation is telling us that the higher we get our values on the one axis, the lower the values on the other axis become. So if you look at this dot here, it's getting just over 6 on the x-axis, but it's getting less than 2 on the y-axis. Whereas this dot here is getting less than 1 on the x-axis, but it's getting nearly 6 on the y-axis. So a negative correlation shows us that as one set of values gets less, the other set of values gets greater. A real life example of this might be if the x-axis represented our maths marks and the y-axis represented the number of hours we spend per day playing Xbox. And you can see that the more hours you play spending Xbox, the more hours a day you spend playing Xbox, the lower your maths marks will be. So that is what a negative correlation looks like. Next up, you might have dots that form a pattern like this. They are clearly forming some sort of line, but it is not a straight line. This we call a non-linear correlation. This actual graph came off a graph looking at people's memory over their lifespan. So when you are a little baby, your memory isn't very good. As you get older, the x-axis represents the age, the y-axis represents memory capacity. As you get older, your memory increases fairly rapidly, but then you get to a certain age around about 60 where your memory starts to decline. So this is called non-linear correlation. Or you could have a whole lot of dots all over the place, and that would represent that there's no correlation at all. The two sets of variables have got no relationship to each other. A real life example might be the x-axis represents your maths marks, the y-axis represents the amount of lettuce that you eat. There's no relationship between those sets of variables. Some people eat very little lettuce and do very well at maths. Some people eat a lot of lettuce and do very well at maths. Makes no difference. We also want to see how strong the correlation is. We don't only want to see whether it's positive or negative or whether it's linear or non-linear. We want to see how strong the correlation is. And we do this by looking at how closely clustered together all the dots are. So here are various scatter plots. You can see in this first scatter plot, it's clearly a positive correlation because it's forming a line with a positive gradient. And you can see that the dots are all quite closely clustered onto this line. That we would call a strong positive correlation. This next one, the dots do seem to be forming a line with a positive gradient, but they're much more spread out. So we would call that a weak positive correlation. This scatter plot in the middle, there's no correlation. The dots are all over the place. This scatter plot over here, the dots are still forming a negative line, but they're quite spread out, so that would be a weak negative correlation. And finally, we have a negative correlation with all the dots pretty closely clustered onto the line, which makes it a strong negative correlation. So, if there is a correlation between variables, so you plot your scatter plot, you just notice there is a correlation, that can mean several things. It can mean that the two variables are somehow related, that maybe the one variable has an effect on the other. If you look back at our original example of heights and weights, I think we can all agree that the taller someone is, the more likely they are to be heavier. So there is a relationship between your height and your weight. However, it is important to note that a correlation does not necessarily mean there is a relationship. It could just be a coincidence. As they say in statistics at university, correlation does not imply causation. Just because something correlates doesn't mean they are actually in any way related. Okay, now let's look at the scatter plot that we drew in example 1. There it is. What kind of correlation would you say that is displaying? Well, it seems to me that the dots are forming a line like this, there, which would mean it's a positive correlation. There is, however, one little outlier here that seems to be off doing its own thing, but the rest of the dots, if we ignore this outlier for a moment, the rest of the dots are forming quite a clear positive line. So that outlier, even though it is on our graph, it doesn't affect the correlation that we can see. Just one outlier doesn't mean that there's no correlation. So there's a moderately strong positive correlation with one outlier. Well, so we can use a scatter plot to see whether there is a correlation and to see whether it's positive or negative and to have some rough idea of how strong it is, but statisticians need a much more precise way of measuring the strength of a correlation. They can't just say, well, it looks to me to be pretty strong. They need a precise way of measuring the strength of a correlation, and the way that they do that is with the correlation coefficient. The correlation coefficient is generated using a complicated formula, which we're going to see just now, and that complicated formula gives us a number that represents the strength of our correlation. That number is always between -1 and 1, and the symbol for this correlation coefficient is R. So if I have a correlation coefficient, I'm going to start in the middle here. If I have a correlation coefficient of 0, it means there is no correlation. If I have a correlation coefficient of 1, that means there's a perfect positive correlation. That would mean if I plotted all those dots on a scatter plot such that they had a correlation coefficient of 1, that would give me a perfectly straight line of dots. If the R is between around about 0.7 and 1, that's a strong positive correlation. If the R is between 0.4 and 0.7, that's a moderate positive correlation. If the R is between 0 and 0.4, that's a weak positive correlation. And if my R is between -0, well, let's just call it 0. If it's between 0 and -0.4, that's a weak negative correlation. If my R is between -0.4 and -0.7, that's a moderate negative correlation. If my R is between -0.7 and -1, that's a strong negative correlation. And if my R is -1, that's a perfect negative correlation. Now, little warning, you'll see when you look in different textbooks and on different websites that the exact boundaries between strong and moderate and weak differ from source to source, but the main principle is that if it's a positive correlation, if it's closer to 1, it's a strong correlation. If it's closer to 0, it's a weaker correlation. And likewise with the negative correlations, if it's closer to -1, it's stronger. If it's closer to 0, it's weaker. So how do we calculate the correlation coefficient? Okay, the formula for calculating the correlation coefficient is this. Yeah, you do know that that's a sheep, eh? That's not a goat. Yes, but it is a good sheep. It's a great sheep. Some might even say it's the greatest sheep of all time. So what does all of this stand for? The x in our equation stands for the values from the one set of data. In our example, that would have been the heights. The y in the equation stands for the values from the other set of data. So in our equation, that would have been the weights. The n stands for the number of pairs of data values. So in our example, that was 10 pairs of data values. And sigma is an instruction to add up, to find the sum of. So here, sigma x means we'd have to find the sum of all the x values. Sigma y means we'd have to find the sum of all the y values. Sigma xy means we'd have to find the sum of all the x's times all the y's. Yes, but thankfully, we seldom have to actually use this equation because your scientific calculator can work out the correlation coefficient for you. Huzzah! Now you're going to have to do some work yourself to go and check out how your particular calculator works out the correlation coefficient. For some of the calculators, the method is described in your textbook. You can go and look it up there. If your calculator is not covered in the textbook, you are going to have to go onto Google. Just type in your calculator's make and model number and correlation coefficient, and you'll find plenty of videos and documents describing exactly how to do it. So let's look at the correlation coefficient for our set of data that we used in our first example. There's the set of data. Now we've got to type all those numbers into my calculator. 162, 52, 178, 60, 181, 78, and we get an answer of 0.71. That indicates a strong positive correlation, which is what we predicted from looking at our scatter plot. Right, what's the next thing we can do with a scatter plot? Well, we can draw a line of best fit. If you have a linear correlation, a line of best fit will be a straight line that goes approximately through the middle of all the points on the scatter plot. In fact, we drew one in our example a little bit earlier. There we go. That red line there is a line of best fit. It's a bit of approximation. One could differ slightly from person to person on exactly where the line of best fit goes, but the general region that the line of best fit would go somewhere here would be pretty standard. Now, when we draw a line of best fit, what we're trying to do is make sure that it goes approximately through the middle of the points, and that we have approximately the same number of points above the line that we have below the line. So you'll see there I've got 5 data points above it, 5 data points below it. All right, so the line of best fit is useful because it allows statisticians to apply all the formulas that work for straight line functions to their set of data. So we can determine the equation of the line of best fit in the same way that we determine the equation of any other straight line function. First, we have to identify 2 points whose coordinates we're pretty certain of that are on the line of best fit. Now, we don't actually have to use data sets that we plotted earlier. We just need to find the coordinates of points that are actually on the line of best fit. So I've gone with these two. 160 and 54 is down here somewhere. 180 and 72 is up here somewhere. Once we've got 2 points with their coordinates, we can work out the gradient of the line, just like we would for a normal straight line. Same formula, same method. There we go. We get a gradient for this particular line of best fit of 0,9. Then our equation looks like this: y plus 0,9x plus c. That is, of course, the standard straight line equation, because the line of best fit is a standard straight line. Now I need to substitute in the x and y coordinates from one of my points so that I can work out what c is. I've gone with 160 and 54. Plug it all in and we get a c of -90. So the overall equation for our line of best fit is y equals 0,9x minus 90. It's all well and good, but you might ask, why would we bother to do that? Who even cares? Well, statisticians care, because once we have an equation for the line of best fit, we can use that equation to make predictions from our set of data, which is a very useful tool. In fact, it's probably the main reason why statisticians do any statistics at all, is to be able to predict from the set of data about other values. So let's do an example from our set of data. We want to use our line of best fit to predict the weight of a person who is 165 centimeters tall. Now, in our set of data, the height was the x values. So we're going to substitute 165 in place of the x in our equation, like that. And we get a weight of 58,5 kilograms. So what we have done is we've said, using our set of data, a person who is 165 centimeters tall, we can predict that their weight would be somewhere around 58,5 kilograms. Again, this is not an exact science, but it does give us a ballpark figure to go on. That should people be conforming to the pattern that we've observed in our data, then a person who's 165 centimeters tall should be approximately 58,5 kilograms in weight. Now, if we make predictions using values within the domain and range of our data, it's called interpolation. This here is interpolation because a height of 165 is within the domain of the heights in our set of data. It's bigger than the smallest number and it's smaller than the biggest number. So this is interpolation. If we make predictions using values from outside the domain or range of our data, it's called extrapolation. For instance, if I wanted to work out the weight of someone who is 220 centimeters tall, that would be extrapolation, because 220 centimeters is well beyond the biggest number in our set of data. Okay, bye-bye.